Okay, so hello everyone, and welcome to our first of these series of webinars on our health report. My name is Michael Scholand, and I work for the IEA 4E Technology Cooperation Program, TCP, on Smart Sustainability in Lighting and Controls, SSLC. And we're here today to have the first of the series of 3 webinars. And this one is on temporal light modulation. And you can see a copy of the report here on the right-hand side. If you haven't already downloaded it from our website, please do so. This is covering this section of the report. And we have 2 speakers with us tonight, 2 of the principal authors of the study, in fact. So Dr. Jennifer Veach is going to speak first. She's talking to us from Canada. And Dr. Veach is a psychological scientist with expertise in environmental psychology and has been a research officer at the National Research Council of Canada since 1992. Jennifer serves as the president of the CIE for the 2023-2027 term. She's a fellow of the National and International Associations in Lighting and Psychology, and she received the Waldron Gold Pin for Applied Illuminating Engineering from the CIE in 2011 and the IES Medal Award in 2018. And just this month, in November 2024, Jennifer was inducted as a fellow into the Royal Society of Canada. Congratulations on that, Jennifer.
Thanks.
And Christophe Martensons is a physicist working in the field of optics and lighting at the CSTB in Grenoble, France. He works for governments, public agencies, and municipalities to improve the quality of lighting installations through a careful consideration of environmental impacts and health and human health effects. He is the current president of CIE France and is a recipient of the 2024 Fresnel Medal awarded by the French Lighting Association. Welcome, Christopher.
Thank you.
Congratulations on the Fresnel Medal. So I'm going to, without further ado, stop sharing and pass over to Jennifer. If you want to take control.
I will do that.
Thank you.
Okay. So it's my pleasure to speak to you first tonight, or this morning, depending on where you are, or this afternoon or this evening, depending on where you are. And then Christophe will take over after I've done my bit. I'm going to give a very quick introduction to the report as a whole. So apologies if you attend the other 2 webinars, because you may see some of this again. This is an updated report. There was a first report by what was then called the Solid State Lighting Annex in 2014, and this is an update of that report. There are still some issues that people have complained about. Of course, there's been a lot of science in the intervening decade, and an increasing recognition that lighting should apply to everybody, but there may be some sensitive populations. So it was time to have a look again at what the literature was showing, to identify features of LED lamps and luminaires that could be improved to lead to better outcomes for people, and also, of course, to take account of the knowledge that we have. So we want to be able to provide some guidance to the lighting industry, but also to public health officials and also the public generally about what they can do themselves or what public health authorities might also want to become involved in. So we want to improve regulations, procurement specifications and standards. And of course, because Christophe and I are both researchers, we want to stimulate the research community to fill in the gaps. Just a note about scope, we're focusing on general lighting products, lamps and luminaires for general lighting, street and road lighting. We're not talking about automotive lighting or light sources that are not lighting products. For example, LEDs that might be used in toys or displays, or a torch that you might carry around if in case the power goes out. None of those are in scope. And want to acknowledge that this is an international effort. It's funded by several governments, This particular report was a collaboration between teams at CSTB, the National Research Council of Canada, where I'm from, and the Australian Radiation Protection and Nuclear Safety Authority. I think I got that right, ARPANSA. And our colleague from ARPANSA will be speaking tomorrow in one of the other webinars. And we worked really well together, collaboratively over a 5-year period. And we were funded by the Australian, Canadian, and French governments, and actually by the Solid State Lighting Annex itself. We reviewed reviews that are published during the last decade since the previous report, published research papers, individual papers if there was no review. And of course, we looked also at standards and guidelines and technical reports that were available to us. So that's the background on how we did this. And now I'm going to move straight into the temporal light modulation effects. So it's really important to understand that when we talk about temporal light modulation, we're talking about the stimulus. It's what a lighting system or a lighting product does. And it's producing a waveform that has time-based modulation, either in terms of intensity, or it could be also chromatic, although there's a lot more evidence for the intensity variations than there are for color-related changes. And just to give you a quick example of what's out there in terms of products that are in use, there's a wide variety. It used to be that everybody used incandescent lamps. That's the upper left there. Nice sinusoidal curve of about a 6% variation in intensity. However, we were also familiar back in the bad old days with T12 fluorescent lamps on magnetic ballasts. They had about a 33% modulation depth, and also a sort of a modified kind of a sine wave. And that was associated for some folks with headaches and eye strain and other kinds of complaints. I and many others stopped studying temporal light modulation. We didn't even call it that in those days, with the advent of electronic ballasts, because pretty much eliminated the problem. But with the advent of LED lighting, what sophisticated people who understood more about electronics than I do found was that there's incredible variation in products, just 2 of which are shown on this slide. One of which had, you can see on the lower left, a really very high, very spiky curve, and another which had almost no variations at all. So suddenly, instead of knowing what you were getting because you had a given light source technology, there's no way of knowing, because there's no sign on the outside of the device as to what's going to happen. And now, of course, we often use pulse width modulation dimming on top of whatever the native TLM is of the light source, and that adds an additional, usually rectangular wave to the variation. So it's pretty complicated kind of phenomenon, and not one that's easily predicted by the average viewer. Now, I want to address one thing that many people say right off, which is this idea that if you can't see the flicker, TLM doesn't even matter. That's simply not true, and I'm going to show you why in later slides. In fact, we don't actually need to be consciously able to report seeing a thing for it to be influencing us. And there's a well-known phenomenon in psychology called blind sight, in which there's a dissociation between perception and consciousness. And you can demonstrate people making behavioral responses to something they can't verbally tell you is actually visible. And the same thing, I believe, happens with respect to temporal light modulation. Now, it's long been known that temporal light modulation affects brain activity. The famous example of this is epilepsy. We know that for a photoepileptic individual, if you expose that person to light that pulses anywhere between 3 hertz and 70 hertz, they may in fact have a seizure, and that could be catastrophic for that individual. So this is not an unknown phenomenon. Interestingly, for people who want to use red flashing lights for fire safety reasons, a red flashing light is probably not the best choice for that, because that actually increases the risk of epilepsy. And that's why nowadays you'll often see warnings such as this one on various kinds of video games and that kind of thing. But there's also historic evidence that the visual system, or the nervous system, pardon me, can respond to temporal light modulation. Early studies we used 60 hertz. That was back in the 1960s. It was pretty much all they had. But once we had electronic ballasts, we could have comparisons between, about 120 hertz in my part of the world, 100 hertz in Europe, and about 40 kilohertz with an electronic ballast, and could show differences in brain responses to being exposed to light sources of those two different types. More recently, there was a study in 2020 that looked at 9 variations using LED light sources operated at different operating frequencies and different modulation depths using pulse width modulation dimming. And they also found that there was alpha suppression, that's a suppression of a particular frequency of brain activity, more so for the 100 hertz source than the 1500 hertz source. And the effect of this was to suggest an increased arousal level for being exposed to 100 hertz as compared to the higher frequency. So even if people aren't reporting that they see the flicker, see flicker or any other visual perception, there may in fact be an effect on brain activity. I was involved in an experiment some years ago in which we looked at EEG responses, not looking at the familiar frequency distribution of brain activity, the alpha, beta, theta bands of brain activity, but instead using an analysis called dipole source moments, which is an index of the strength of the brain activity. And what we found was that both the location and the strength of the activity varied in response to TLM conditions. But it was pretty complicated in that the responses that we found also depended on the nature of the task that people were doing and its difficulty. So you would see a bigger effect on a simpler task, probably because people were already having to work harder on that more difficult task. And there's a citation there that you can go and chase down if you're particularly keen. Now, it's also been known, and this is 40-year-old data from Arnold Wilkins, that eye movements are disrupted by temporal light modulation. In the day, back in the 1980s, he was comparing the old sort of visual display terminals with cathode ray tubes operating at 50 hertz versus others that he had modified to work at 100 hertz. But he also had fluorescent room lighting. His comparison at that time was between 100 hertz, this of course was in the UK, to 20 kilohertz, which would be the typical of an electronic ballast at that time, there was a very new technology right then. And what he found was that for the lower frequency in each comparison, there were larger saccades, so larger eye movements happening. And that didn't mean that they were reading better. What it meant was that they probably had to then overcorrect with a corrective saccade to get in all of the information. And what that does is it increases fatigue and it slows performance. And Arnold's hypothesis is that this kind of disruption is actually occurring because there's neural noise, and that neural noise is actually increasing the cognitive difficulty of processing the information that you're trying to read. Now, moving to other kinds of phenomena besides the brain activity, we're familiar with the phrase these days, temporal light artifacts, which is not a super great phrase in my mind, because people often seem to equate that with the temporal light modulation that the light source gives. These temporal light artifacts, as people call them, are really visual perception effects. So there's flicker, which of course is a perception that we have that the light source itself is varying. You may see it in a friendly way with flames that flicker, or perhaps a less friendly way in a light source where you can actually visibly see the change in luminance. You can also take a nice picture of it if you go down to capturing it with a cell phone. Now, another visual perception that gets a lot of attention is the stroboscopic effect, which is a change in motion perception. So for the stroboscopic effect, you need a light source that has temporal light modulation, and you need an object that is moving. Now, in the bad old days, we knew about this problem in the context of industrial machinery. More recently, it's been studied with respect to the kinds of motion that can happen in office-type environments, so much slower rate And it has to be said, a much less serious consequence of an error, since you really don't want to get caught in moving machinery that looks stationary. I'm going to talk for a minute about an experiment that Christoph and I did a few years ago with funding from the Solid State Lighting Annex, in which we compared the visibility of the stroboscopic effect under 5 different commercially available light sources, which are photographed here. So we indexed these using the, I hope, fairly well-known stroboscopic visibility measure, which is an integrated index that Christoph's going to talk about a little bit later. A light source that had an SVM of 0, so almost no temporal light modulation, would show the disk when the white dot is circulating around at 4 meters per second, it would show that as a white smudge. And then with increasing amounts of temporal light modulation, you get an increase in the index, the SVM. The highest light source that we had an SVM of about 3. And you can see on the far right of this slide that to a person looking at that, it looked like a series of discrete white dots moving around as the disk circulated. And generally speaking, it's thought that stroboscopic motion is visible up to about a maximum of 2000 hertz. Now, the study that we did, we had a total of 85 people in France and Canada. And what we found, as you would expect, is that the detection of the motion of the stroboscopic motion increased with the increase in stroboscopic visibility measure. And it was a nice sort of exposure response curve in response to that. And I'm going to come back to this a little bit later, we also assessed people for their sensitivity to visual stress. We didn't find differences in their detection of stroboscopic motion as a function of sensitivity, but we did have a different other finding, which I will come back to a little bit later. That's a teaser. The third kind of visual perception effect is the phantom array effect. And it's a little more complicated to explain, but it's diagrammed here in this lovely diagram from Naomi Miller. So imagine for the moment that you're the person seated in the center here, and you're moving your eyes from one red dot on the left across the illuminated slit in the middle of this black screen to the other red dot. And what you would see if there's temporal light modulation in the light source of that slit is a pattern that looks like what you're seeing on the bottom here. That would be dark across the left-hand part of the image because there's nothing there. And then as soon as your eye crosses over the modulating white strip, you're going to get retinal patterns that are going to give you a pattern as you move your eye across to where the other red dot is on the right. And this is a phenomenon that many of us have experienced when driving at night, because you can often see this as you look at the rear lights in the car ahead of you. Now, I did say we're not talking about automotive lighting in this presentation, but that's just an example of the ubiquitousness of this problem. And what's very interesting about it is that it can occur across a very wide frequency range, for TLM down around the 80 hertz level, up to as high for some people as 11,000 hertz. And it occurs when the eye is making these large saccades because of these spatially separated retinal images, which are understandably pretty distracting to people. Now, there's been an interesting explosion recently in research related to the phantom ray, which is really great to see. I know Christoph's been involved in some of it, and he's going to talk about some as well when his turn comes. I'm going to use this slide that I obtained from Naomi Miller at Pacific Northwest National Lab, just to illustrate differences between stroboscopic motion and the phantom array. So these are a set of curves showing the detectability or the visibility rating on a scale from 0 to 6 of either stroboscopic motion or the phantom array in response to exposure to a wide variety of different stimuli. These ones are all square waves, differing in the duty cycle and the modulation depth. So imagining that we're using light sources that are using pulse width modulation. And what's important for you to recognize here is that they're totally different. So we had hoped at one time that we could have one quantity that would predict both of these things, but it's quite apparent that that's not going to work. They're simply not the same thing. And at the time this paper was first published online, there was no predictor for the phantom array, although the same team has more recently published a possible quantity that might predict phantom array visibility. Now I'm going to shift a bit from perceptual effects to more complex kinds of performance effects. This is a reference to a very old study that I did with a student many years ago. She's, of course, no longer a student now. She's a psychologist in practice in Montreal. But at the time, we were interested in the response of people to a comparison between magnetic ballasts and electronic ballasts, and people's ability to do this Landau ring task in which you detect the direction of the gap in the rings. We had only young participants, and even those young participants could only showed a difference between reading performance under the magnetic and the electronic ballasts on the most demanding tasks. And this was with the repeated measures research design. So it can be very difficult to detect a performance effect of TLM because the effects can be small, especially in the general population, which does argue that we need to focus a little more on the very sensitive people to get a handle on what the effect could be, because I hope that we all care about providing good lighting conditions for everybody. Similarly, a group in Colombia, Yayin et al., also found better visual performance on a paper task with a similar kind of comparison between magnetic and electronic ballasts for fluorescent light. And they also repeated that finding. So it's really nice to see this kind of thing being replicated in solid experiments. And they also noted that there are very wide individual differences. Some people could really sort of perform well no matter what. Other people had a much bigger performance decrement under the condition with the magnetic ballasts. My colleague Guy Newsham and I, in the study shown on the right here, used a psychophysical task, kind of like a video game. And people were looking at this on a CRT monitor, which unfortunately was, the mid-1990s. All we had were those horrible old cathode ray tube monitors that operated at about 60 hertz. But everybody had the same monitor. So we were comparing ambient lighting conditions. And what we found was that, in fact, what you'll see here on this chart is that better performance is always high, so faster performance under the electronic ballasts than under the magnetic ballasts. But that effect was bigger when the task was easy than when the task was complicated. So again, it can be difficult to find these effects, but nonetheless, they do occur. We also found that Guy and I in that same study that there were effects of reading and writing in response to temporal light modulation. When we were comparing people with electronic ballasts versus working under magnetic ballasts, they tended to write words that were longer when they were writing a creative writing story. They wrote more characters in their stories, and they also attempted more questions on a complicated reading comprehension test. So here we have quite complicated kinds of tasks being affected by the temporal light modulation of a light source. Now, what about individual differences in sensitivity, which I've been referring to along the way? Well, it's fairly well known that this light sensitivity can be a characteristic of people who have a propensity to have headaches, and especially people who have migraine headaches. Not all people who experience migraines have triggers that are light related, but some do. There is some evidence that sensitivity to that problem tends to get less as we get old. So hence many of the studies have tended to focus on young people. There is a diagnostic test called pattern glare sensitivity, which was developed by Arnold Wilkins and his colleague, Mr. Evans. And it has been associated with headache and visual disturbances while reading. And the test is one that is probably not going to work on your monitor right now because this is fairly low resolution. But if you were doing the test, you would be shown each of these stripy patterns one at a time, and you would be asked to report whether you see any kind of visual disturbances, blur, whether it would be uncomfortable, whether it would seem that the stripes were moving at all. And in particular, that middle one is the target that is most associated with these problems. the one on the right, it's actually very difficult to administer the test well enough to get the intended visual angle. So that tends to be a bit messy. Fortunately, there's also a simpler way to assess sensitivity now. There's a 9-question item questionnaire called the Leiden Visual Sensitivity Scale, which also correlates really well with pattern glare sensitivity, but it's a lot easier to administer. So researchers are tending to, I think, shift a little bit to using that scale instead of the more complicated pattern glare sensitivity test. So what about these sensitive people? Well, it's long been known that some people complain of having headache and eye strain in response to certain kinds of lighting conditions. Historically, with magnetic ballasts, we heard that a lot. It's a fairly slow onset, and it seems to be mostly associated with the range of 100 to 120 hertz. But not everybody's affected by it. We know that as well. Back in the late 80s, Arnold Wilkins and a team did a field study of fluorescent systems. You'll notice a theme here. A lot of the past research is a comparison between magnetic ballasts and electronic ballasts. And what they found in this really nice ABA design, where they would swap out the control gear for the fluorescent lighting system at night, and so people didn't know what the system was at any given time. What they found was that when the high frequency lighting was in place, the people who were prone to having headaches anyway, so in the baseline period where they've done nothing to the lighting, they found out who was likely to have headaches. Those people tended to have fewer headaches under the high frequency lighting condition. And interestingly, they tended to use the lighting more when it was with the high frequency ballast as well. And interestingly, it was a building that had several floors, and the upper floors had more daylight because there was less shading from adjacent buildings. And on the upper floors, people also tended to have fewer headaches. That would be in the floors in the places with more daylight. Now, more recently, a team in the Netherlands did a field study of LEDs operating with different TLM characteristics, and they had chosen stroboscopic visibility measures of about 0.47 and 1.34. And the 1.34 they chose in order to be somewhat similar to certain magnetic ballast temporal light modulation profiles. Now, in their field study, which was also a well-conducted ABA design, it was in a big open plan space with lots of windows. Now, they found no effect of the TLM manipulation on headache or eye strain reports. But that being said, there was lots of daylight in the space, and they didn't have any information about where people had been. So they didn't know if the person responding had been right next to the window and maybe primarily experienced daylight most of the day, or much deeper into the space where there was perhaps less daylight and therefore more propensity for the SVM manipulation to happen. They also didn't have any data on individual sensitivity. So they couldn't do the kind of analysis that Wilkins did in focusing on the effects of the temporal light modulation on the sensitive people. And unfortunately, you can't go backwards and recreate information that you didn't collect the first time. So we can't make a simple A to B comparison between these two studies. And this is where I come back to the study that Christoph and I did. We did also assess pattern glare sensitivity in order to do a subgroup analysis. And as I mentioned, we didn't find any differences in the sensitivity to stroboscopic motion between the two groups. But what we did find when people were asked to rate the annoyingness of the light sources, the people who were high in pattern glare sensitivity, so the sensitive individuals, did tend to find the conditions more annoying when they were higher in temporal light modulation. They had a higher SVM value. And this is really interesting because they had seen these light sources 10 times, but only for a very short time each time, about 20 seconds. So if this could be annoying after a 20-second exposure, imagine what it might be like for someone who's exposed to that lighting condition for hours at a time. Now, just this last week, a new study was published, so it didn't appear in the report. It's kind of cheating for me to even mention it, except that it's so apt to what we're talking about. A group, again, Pacific Northwest National Lab, have published a study in which they compared migraineurs, people who experience migraine headaches, and people who don't, for their phantom array visibility to a variety of different temporal light modulation waveforms. There were 85 conditions in the experiment. And what they found was that the people who have a tendency to experience migraines did tend to find that the phantom array was more visible, and they were able to detect the phantom array at much higher frequencies than the people who didn't have a tendency to have migraines. Those same individuals were also asked about their experiences in everyday life. They reported being more annoyed by phantom array phenomena in their everyday life. And when asked 4 hours after the experiment, they reported more adverse effects of having been in the experiment. So this does give us this clue that for people who are sensitive, this is a real problem, and it's something that we should be paying attention to. So to wrap up my part of this presentation, there's an emerging logical chain here. We know that TLM is photochemically detected at the eye. There are these modulated neural systems that reach the brain and they cause neural noise. They don't contribute information to the visual image, and processing that takes cognitive resources, increases the brain activity and the blood flow to the brain. It disrupts saccades, interferes with visual performance, can give rise to visual perceptions that people can report. And all of those things together can reduce cognitive performance, can manifest in eye strain, headache, and fatigue. And we seem to see that there are sensitive individuals that might react sooner or more intensely to those problems. So it all does follow a nice, sort of interesting and compelling, I think, intellectual or logical chain. Now, there is more that we need to know. We don't know much about what's the population norm for sensitivity, how many people in the population are sensitive. We do know that there are some individuals who are very sensitive. And if you want to read more about that, you can read the interesting correspondence that Naomi Miller sent to Lighting Research and Technology, which was also just published last week. There's some other specific research needs that we outline in the report that I commend to you. But I would particularly say that for my money, I think we need more long-term data. There's quite a lot of very short-term exposures to many stimuli in one study, like the 85 that PNNL tested recently. But it would be very interesting to see more about what the consequences are of longer-term exposures than these very short, perceptually focused ones. There is a need as well to pay attention to the standardization of framework. I was part of developing this with the CIE at a workshop we had 7 years ago now. We had hoped back then that we could have a nice purple box with a single metric that would predict everything, but I think we're seeing now that that's not possible. But the other thing that is beyond a research need, which is really a discussion to be had among people in the industry and other stakeholders, is this issue of societal values and achieving our consensus about what's our risk tolerance. How much of a problem does it need to be for how many people in order to choose to make a difference or to spend a little bit more money to design or purchase a product? There's a cost-benefit discussion to be had there that I'm not currently hearing. We did in the report make some policy recommendations. We really would like to see manufacturers target TLM and its reduction as much as possible, because that would really solve the problem for everybody. We also would like to see standardization bodies make sure that we have the appropriate range of expertise and not just people with a technical knowledge of how to design a driver for an LED light source. And also perhaps to consider the lived experience or the other sort of allied stakeholders as part of that process. We do encourage a little more interaction as well between energy regulators and public health regulators. Again, there are some parts of the world, and I know Christoph's going to talk about this a bit, where the idea of including a health-related performance specification as part of an energy recommendation or regulation is perfectly accepted. I do not live in one of those parts of the world, so I'd like to see that kind of cross communication happening a little bit more. And that's where I will stop, and I will turn over the baton to Christoph.
Great. Thank you, Jennifer. So I will share my screen and start where you stopped exactly. So just give me the feedback if you see the slides.
Yes, we do.
Okay, thank you.
Yep.
So I will give you, after this really comprehensive review that Jennifer gave, some details about measurements and standards and the metrics about temporal light modulation. So in the old times, we had a lot of historical indices, historical metrics, and they were used systematically to describe temporal light modulation and even flicker. And the main problem that we have with those metrics, they are modulation frequency, flicker percent, flicker index. These quantities are linked to the waveform, which is, as Jennifer said, the stimulus and not the response or the perception. So we had this type of problem. And in addition, when we switched to LEDs, those quantities were very difficult to apply because the waveforms, the temporal fluctuations of the light outputs were very complicated sometimes. So not easy to describe by a single frequency, for instance, or a single modulation percent because of various shapes and multiple frequencies in the signal. So the latest guidelines were made by the CIE and the IEC, and we found the latest measurement guideline in a technical note from the CIE published in 2021. And this will be replaced by a new technical report, very comprehensive, that should be published in 2025 by the working group, the technical committee, 289 of the CIE. Now we have two technical reports from the IEC defining the SVM metric for the visibility of the stroboscopic effects and the PSTLM metric to describe the visibility of flicker. And in 2022, the CIE published a technical report defining all those visual perceptions effects, flicker, temporal flicker, the stroboscopic effect, and the phantom array effects. They were defined in this publication. So let's start by flicker. Flicker is now described by the CIE and the IEC by PSTLM, which is actually a very old metric coming from the IEC voltage flicker meter. It was a quantity designed to test voltage fluctuations. And at the time, the best way to test voltage fluctuations was to have a viewer looking at an incandescent lamp and detecting fluctuations in the light output of this lamp. So it's a very complicated calculation carried out in the time domain. So it uses 3 minutes of the temporal light waveform of a lamp, and then several steps in the calculations. And at the foundation of the calculation, we found this curve on the right side, which actually derives from old work from the 50s, from the Lang. And this curve peaks at about 10 hertz. It's quite a narrow peak, and it explains that the flicker, the direct flicker that you can experience in lighting is very, very visible and actually very bothering at around 10 hertz. The problem with this PSTLM index is that it's based on old research on visual conditions that are not very common. At the time, this index was determined using a 2-degree field, so very narrow field of view, corresponding to a small light source seen from a few meter distance, with bright surrounding, sharp edge. And we know that flicker is very dependent on the position of the source in the field of view. And there's also a statistical evaluation step in the calculation of PSTLM, which is very tricky to understand because it's a formula with a lot of coefficients that unfortunately nobody can explain anymore. And more importantly, I would say, it's always difficult to set a proper limit on PSTLM because we don't know the response curve. What is PSTLM versus temporal light modulation versus PSTLM visibility? So it's difficult to set a limit if we don't have this curve. There are less known facts on flicker, and I just wanted to mention that to tell you that PSTLM reflects flicker in a single condition, whereas flicker does vary a lot with the brightness and with the contrast as well. Here, there's a photo of a small, very simple experiment where you have two gray disks flickering exactly at the same time. So two flickering sources. And the surrounding of these sources are dark on the left and bright on the right. So the main thing from this experiment is that the surrounding of the flicker source creates a phase lag in the perception. It completely changes the perception of flicker. And it's very spectacular when those two stimuli run at the same time, because you see strange effects of phase lags, whereas the temporal light modulation is strictly identical. Flicker is not perceived in the same way whether you're adapted to bright or dark condition. So basically, there's a rule of thumb saying that if you are 10 times darker in the environment, flicker perception is slower. And actually, flicker depends on the spectral distribution of the stimulus itself. And as I said, it depends on the position of the source in your field of view. So the peripheral vision is sensitive to much faster phenomenon. So much faster frequency, higher frequencies. So this is typical, this curve is very well known because it was one of the curves derived in 1958 by DeLange. And this curve was, at least the bright one on the top, was used in the PSTLM computation. It's important to notice here that if you go from bright to dark condition, you lose this peak. And at the time, it was very strange to observe this peak. Now we are used to it. But this peak appears only in bright conditions, and it was called at the time a resonance peak, something that is amplified by the visual system that would not occur in dark environment. And this resonance is really correlated with the highest level of annoyance and discomfort experienced from direct flicker at about 10 Hertz. And flicker varies with color, so the spectral distribution of the source. And it globally increases from red to blue in terms of absolute visibility, but the shape also changes with the color. So for example, with a special type of green at about 512 micrometers wavelengths, the peak wavelengths here, you don't get a very pronounced resonance peak in the flicker perception. And I think it's related to the how our retina is cabled, really, the physiology of the retina and the processing of light. I would say low-level processing of light by photoreceptors. So if we move to SVM, the stroboscopic visibility index, it's a more recent metric. It was defined by teams from Philips in 2015. At least it was defined before, but published in a journal article in 2015. And it uses an experimentally based sensitivity curve that you can see here on the left side, peaking not far from 100 Hertz. So this stroboscopic effect is related to the motion of the hand. So the peak is very pronounced, and you can see that it was centered at 100 Hertz, which at the time of fluorescent source was the highest the most visible frequency in the temporal light modulation waveform of lamp. So it was very common and still common to see 100 hertz modulation frequency, which is dominant. The SVM is computed in a frequency domain. It doesn't rely on a time calculation, so you have to perform a Fourier decomposition of the waveform and apply a formula here based on this sensitivity curve. And we do have a stimulus response curve that Jennifer and I derived a few years ago, slightly different from the one that was derived originally by the Signify team. But this curve is very important because when you have the stimulus response curve, you can set a limit exactly with the proportion of people that you want not to experience an effect. So you have a quantitative basis to fix a limit, which we don't have with Flickr at the time, with PSTLM. So in the eco-design regulation in Europe, so eco-design is mainly a regulation aimed at saving energy, so energy efficiency, and limiting the environmental impacts of lighting. And as Jennifer said, it's very interesting that temporal light modulation limits were introduced, especially a very low limit in SVM. We are now at 0.4, because at 0.4, if I go backward, you start seeing a rapid nonlinear increase in the response to stroboscopic effect. So it's a protective limit that was set to avoid that a lot of people experience the vision of the stroboscopic effect. I would say that with the 0.4 level, about 10 to 15% of the people see the stroboscopic effect. The impact of this eco-design regulation was quite significant in Europe. There was a paper published this year comparing commercial lamps that were bought before the implementation of this regulation, at least with the limits in SVM, so the latest version of the regulation, and new lamps bought after. And the reduction in SVM, which is called MVS here, but it's the same quantity, is dramatic. It's really, it really improved. And virtually there's no high SVM lamp on the market in Europe nowadays. Now the phantom array. So I will not explain this because Jennifer already explained how multiple images are created when you move your eyes in front of a temporal light modulation source. We have different sensitivity models for the phantom array. So the consensus is not exactly reached in this area. However, many research teams, most of them, found a maximum just below 1000 hertz, let's say between 500 hertz and 1000 hertz, with a peak, I would say, between 500 and 600 hertz. So this phantom array effect is sensitive at much higher frequencies than flicker and the stroboscopic effect. So it goes up to very high modulation frequencies. We have a new metric called PAVM, but it was only proposed by one team and needs further validation and, of course, some standardization to agree on that. Our team at CSTB worked with TUE and RISE in Sweden to derive phantom array sensitivity curve in terms of visibility threshold. So we found, for example, if you look at the graph for a warm light, we found a peak at 600 hertz and a threshold of about 6% when it's a pure sine wave. So the effect is quite important because even with 6% of modulation at 600 hertz with a pure sine wave, you have half of the people seeing the effect, half of the time. So probability of 50% detection of the phantom array. And PAVM, published by Naomi Miller's team at PNNL, is almost identical, but not exactly the same shape, but the global behavior is identical with a peak here at a little above 600 hertz. And she derived a dose response curve, which is very useful because it's possible to set limits. And the calculation of PAVM is inspired by these SVM. It's a frequency domain metric relying on Fourier transform. The phantom array has very difficult features also to assess the dependence with the color of the light and the change in the threshold frequency, the highest frequency where you can perceive. And this higher threshold frequency was studied extensively by a Korean team. And they also published interesting papers on the influence of light. So red, for example, when you have red modulated light, it's detected at much higher frequency than blue or violet light, for instance. This has consequences for all type of colored lights in architectural lighting or automotive lighting, even if it was not in our scope. To measure TLM in a lab, and when you run a test lab for TLM, you need special equipment, you need a special protocol for measuring things, and you need algorithms to compute the indices, PSTLM and SVM. You need to be very careful at those three levels, I would say, because those calculations, those measurements are quite new. And it's important to point out a lot of metrological issues. And my lab with some other partners just completed a European project on the issue of measuring TLM and measuring PSTLM and SVM, the associated index. So it's a complicated problem, and we found actually a lot of problems, but we really improved what can be done to reduce the measurement uncertainty. So we should check, when you measure the waveform, you should check the sample rate, the linearity, the dynamic range of your equipment, the analog to digital resolution, the number of bits you have in your signal. And once you have acquired the waveform, you need to apply a proper windowing and zero padding procedure treatment to help reduce some glitches. And also we found out that numerical algorithms that were distributed by the IEC to compute PSTLM and SVM, so these are MATLAB procedures, they are not the most reliable. And in this MATLM project, we found a lot of numerical patches that could be applied to really improve the calculation of PSTLM and SVM. So here on this slide, you have some examples, some publications that were directly written following the findings of this MATLM project. This one here by Noémie Miller's team was not in MATLM, but it's really important also, showing some issues with the calculation. We currently run within the annex, the Fourier SSLC annex, an interlaboratory comparison test. And the first report was published, also showing that there are issues in the measurements, especially PSTLM, because it is subject to large effects of the power supply and not the lamp itself, which is a problem because when you want to assess flicker, you want to assess flicker from your lamp and not from the power supply. So PSTLM is very good for testing that, actually. It was originally a metric used for quantifying voltage fluctuations and the immunity of equipment to voltage fluctuations. So since it's very sensitive to that, we believe that a better flicker metric for the quality of light and not the quality of the power supply is needed. Portable equipment can give you some good ideas about flicker and stroboscopic effect, and they can measure the waveform, but there is a large influence of daylight. And also, we don't really know how different waveform of light can combine and alter the result. So these equipment have to be used very close to the light source, but we don't really have a measurement standard for that. And now I would like to thank you for your attention, and I will stop sharing and we can move to the question and answers.
Super. Well, Christophe, there is a question that came in while you were speaking. Do you see the Q&A with a little red number 1 on it?
Oh, yes.
Yeah. So I think you can click that and maybe read Alex's
Okay.
question. Yeah.
Okay, the WELL standards are taking into account Flickr in relation of well-being of human in the workplace. Would you say that the requirements are not in line with the results that you are showing? Don't recall which requirements are in place within the WELL standard. I'm sure it's Flickr and the stroboscopic effect, and I don't know the thresholds that are used. But it's still a very good thing that the WELL standards include Flickr and temporal light modulation in general. I think it's Flickr and the stroboscopic effect. So maybe Alex has additional details, but overall, I would say that those certifications apply to buildings, and they include lightings in great details, especially WELL, which is targeted to the well-being of occupants. So it's a very good thing that temporal light modulation is included, but I don't know to what extent it is included yet, but it's in the right direction, I would say.
Yeah, I would say that it would be, and I also don't remember what they are saying. It would be astounding if it currently included anything related to the phantom array, because until extremely recently, there was no way to quantify it at all. And as Christophe pointed out, it's very new and it requires validation. So it's a bit soon for that to be represented there. But one good thing about WELL and other kinds of certifications is that, you know, it's like standards, right? Nothing is carved in stone. Things get updated on a regular basis. So as new information comes in, I'm sure it'll get incorporated.
I see more details on the question
Yes.
and answers here.
Okay.
Okay, there's a target in Wells called Manage Flickr, which is good. So Flickr is just, we don't know at this point if Flickr refers to all types of temporal light artifacts or just Flickr. That's the problem with the old standards. But when I see the 3 criteria there, the last one is really about PSTLM, so direct Flickr, and SVM, stroboscopic visibility measure. One is the limit we have in Europe, but as I said, we don't really know how good it is because we don't have the stimulus response curve. SVM 0.6, well, it's a new threshold because in Europe we had 0.9, then we moved down to 0.4, and here I'm seeing 0.6. I don't know why.
Yeah. I think the other thing to bear in mind, and this is true for the California Title 24 one as well, is that all of those, including the European regulations, apply to products at full power. And so if there's dimming that's going to be applied, which is true for many, many, many light sources, many control systems, if it's pulse width modulation, then what the people in the space are being exposed to is whatever the outcome is of a PWM condition for the dimming. So the theoretical value it might pass for SVM if there's no dimming, but that's not going to be what happens on a day-to-day basis for people in the space. This is not to fault WELL or anybody else because we don't have values that take dimming into account. That's an area where, again, we need some more attention and some more consideration to where do those trade-off lies? How important is it to us to save the energy with the dimming versus the risk that we're adding by creating some temporal light modulation?
Great, thank you. Thank you both. There's the next question is from Simon Perkins. Can you see that one in the Q&A?
Oh, yes. With the work carried out, what level of adaptation luminance was used? Are there changes in the visual system moves from photopic to scotopic levels of luminance? Of course, it's really a well-proven effect that all the visual effects, I don't know about the non-visual or other outcomes about headaches or even visual performance, but as far as vision is concerned, it might be not as strong as color vision varies, between scotopic and photopic, so between dark adaptation and bright adaptation, but all the indications that we have about, especially flicker, show that it's a strong variation.
Mm-hmm. And it has to be noted that a lot of the literature on phantom array probably was taking place, well, at least under mesopic conditions, if not actually scotopic conditions. A lot of the initial work on phantom array came from people who were interested in what was going on with automotive lighting.
So phantom array seems to be much more visible in the dark with a bright source.
Mm-hmm.
Flicker seems to be more visible with a bright source on the side of the field of view, but in a bright adapted vision. As I said, this sort of resonance peak around 10 hertz, which is very bad flicker. Nobody wants that in lighting, but it's really happening at photopic levels.
Mm-hmm.
The stroboscopic effect was, as the SVM was made to reflect the visibility in bright environments, office lighting environment, not outdoor, but indoor office lighting conditions.
Great.
Oh, another question.
Mm-hmm.
Interested in the varying visibility of TLM with varying levels of daylighting. Would you propose this is a function of the artificial modulation becoming relatively smaller compared to the higher levels created by the daylighting? Or perhaps spectrally influenced? No, it's like you said, Wes, it's the first element. It really pushes the average level, so it makes the modulation looks smaller in terms of contrast. So the modulation percent would be smaller.
Yes.
And the visibility would follow with smaller levels of visibility.
Yeah.
Influence, we don't know. We don't know if the spectrum of daylight, which is rich in short and long wavelength, would influence the perception of temporal light modulation. It's a good point, actually.
Although I think, well, the intensity difference is so much greater, though, that I think that would completely overwhelm everything else.
Yeah.
The last question here, does sensitivity change, possibly decrease with increased exposure time? That's one of those questions that we don't really know yet. There's very little evidence from studies that have exposures longer than at best a few minutes. One of our own studies, I think, is one of the longest out there, and we think had 15 minutes of exposure, but we were still seeing effects. There's also some anecdotal evidence, and I'll stress that it's anecdotal, including from some TLM researchers I'm acquainted with, who've spent a lot of time being exposed to varying TLM conditions, who have self-reported that their own sensitivity has increased over time. So that's something that we need more systematic evidence to look at. But if so, that would be particularly unpleasant for just about everybody, because we're all being exposed to it these days.
We're a little bit over time, but we still have a large number of participants attending, so it's great everyone's staying online. Are there any other questions from the audience? Anyone want to put their hand up and just ask their question verbally? Because sometimes it's challenging to put things across clearly in sentences, although the people who've asked questions tonight have been very clear. So grateful for that. But yeah, feel free to raise your hand if you'd like to ask a question live. And just while people are thinking of that, just to note that we will be posting this recording on our website, as well as a copy of the slides. So you'll be able to click on the hyperlinks in the presentation for further research, further information. All right. Well, I'm not seeing any hands or any other questions. So we just say thank you, Christopher. Thank you, Jennifer. It's been fantastic, very helpful, and
Yes.
very good presentation. And yeah, and thank you everyone for participating today. And with this, I will close the webinar. Thank you.
Thank you.
Good day, good evening.
Bye-bye.
Bye-bye.
Bye.